Here's a work solution to number 5. Since I didn't want to do this in class, we have the position is s is given by t over 1 plus t squared. And their version of the problem goes from t equals 0 to t equals 8, but I'm more interested in letting t be negative because we can observe some more interesting stuff about this particular function. Okay, so the first thing, they start asking about the velocity. The first thing is that the velocity is the derivative of position. And we got to use the quotient rule. Derivative of the top is 1. 1 plus t squared is the bottom, left alone, minus the top left alone times the derivative of the bottom, which is 2t, all over the bottom squared. Okay. And so that's going to simplify to, we get 1 plus t squared, but then minus 2t squared. So we get 1 minus t squared over 1 plus t squared squared. Okay. So that is our velocity function. So for example, if they asked us what was like the velocity at 3, for example, we can do that. It's just going to be 1 minus 9 over 1 plus 9 squared, which is minus 8 over 100, or minus 0.08. Okay. So that's an easy thing to answer once you got the velocity. Much more interesting is where is, or when is it momentarily at rest? Okay. That is a mystery t, but where velocity is equal to 0. Okay, so in other words, we're going to take 0 and set it equal to this quantity. Oops. It's getting squirrely on me. I don't know why it's doing weird things. Okay, just copy that. Okay, so here's one of the first really important things. If you're taking a fraction, a rational function like this, and you're setting it equal to 0, the only way that can be true is if the numerator is equal to 0. That's much simpler than most people expect. You can ignore the denominator. Now, let's think about that for a sec. What about the denominator being 0? Well, that wouldn't cause the whole thing to be 0. It would cause the whole thing not to exist. Okay, so we will, I'm going to warn you, we will often have to worry about the denominator equal to 0. But here, what's going on? You've got 1 plus a square. That's always a positive number. That's never 0, and then you're squaring it, so it's certainly not 0. Okay, so here the denom is never 0. So very often it makes sense to worry about, ooh, there could be like a does not exist for the derivative. Does that need like infinite velocity or something like that? Could happen. Shouldn't happen in a realistic model. But it doesn't happen here at all. So we're not going to have to worry about that. So in other words, we're just looking at 1 minus t squared equals 0. Now remember, since there's only one t in that equation, you don't have to factor that. We can, and we will in a minute, for one method of doing a sign chart. But you can just move everything over. T equals the square root of 1, but plus or minus. So it's just going to be plus or minus 1. And that's one reason why I wanted to do the version where we actually allow negative t, because otherwise you don't see both of those things. Okay, it's going to turn out that those are going to be turnarounds. Okay, so let's see. I stupidly had an S number line ready here, but I didn't have a T number line ready. Let me just try and get that up here. So here's a T number line. Good enough. And let me just put a T here. Okay. So we're going to make a sign chart here. Eventually we're going to do the side-to-side view picture that we want to do that as well. But here, let's look at T here. And so we now know at T equals plus or minus 1, so I'll put those conveniently here and here. Okay. Plus or minus 1, we get 0 for the function, so I'm going to put a 0 right here and a 0 right here. Okay, I know it's going to come out looking crappy, but I didn't want to use the by hand graphing. Okay, so we just need to know what happens over here. Is it plus or minus? Over here is a plus or minus. Over here is a plus or minus. Because what we want to know is when is the particle going left? That's v less than 0. Or right? That's v greater than 0. Okay, so we need a sign chart. There's two ways to do that. One method is to go ahead and factor it. So again, this looks really complicated to do a sign chart for, but one of the things that is important about the denominator here, not only is it never 0, it's never even negative. Whatever the sign is for 1 minus t squared, and that's going to be positive and negative, it can be both. If I divide by a positive number, the square of this positive number, that's just never going to change the sign. Okay, so we really just need 1 minus t squared. And so here's where it is useful to factor it. That's 1 minus t, 1 plus t. Okay, and often you are going to be factoring these guys, so sometimes you'll have this anyway. Turns out we didn't absolutely need to here, but often you'll have it factored already because you solved it equal to 0. Okay, so what we can do is to do separate sign charts for 1 minus t and 1 plus t. Those are very simple because they're just linear functions. Okay, then combine them. Okay, so that's a strategy that some people were using before on a similar problem. Let me show you an even simpler strategy that's often helpful. We know that it's 0 at minus 1 and 0 plus 1. So whatever it is to the left of minus 1, it's just one sign there. It can't change because we know all the places it can change. And you can only change at a 0 or possibly at a DNE. And we know there's no DNEs, and we know these are both of the zeros. So we just have to sample any one point out here, and here, and here. So just 3 points. Okay. So the plug-in strategy, okay, as opposed to this separate sign chart strategy, which I won't pursue. We just look. Let's see. V of, let's say, minus 2. Actually, minus 3, because we're going to want that anyway. Well, we might want that anyway. V of minus 3. It's very similar to the calculation we did up here. Okay, we're just going to plug in minus 3 into here. Actually, let's see what happens. Oh, let's look at what happens here. If I plug in a minus for t, does it matter? Hey, both of them are squared. It's going to be exactly this, so I can actually copy it and not even modify it. Because minus 3 quantity squared is 9. Okay, so we actually get exactly that same number, minus 0.08. In any case, it's negative. Okay, so we're going to get minuses out here. Let me put in some minuses. Minus, 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 minus. Okay, V of 3, we already did that calculation a little while ago. These are going to be minuses as well, just lower, because I put it down lower. And then in between here, what do you get? Well, just plug in V of, what's the simplest number possible? Go away. Okay, I don't want that. Okay. What's the simplest number possible? 0. Okay, we plug that back into the velocity function. 1 over 1, oh, that's 1. And that's certainly positive. Okay, so that's often the quickest strategy, is once you've found the zeros, which are the possible turnarounds, just plug in a few values and you get minus 0 plus. Or minus 0 plus 0 minus. Okay, so now we know which way it's going. It starts out heading left. Then it turns to the right, then it goes to the left. Remember, this is the t number line. This is when stuff happens. This is when. Now we want to put into the where picture. What does it actually look like when you look at it from the side? This is what happens as you're looking at the clock and you're recording like as what happens in terms of a schedule or like an agenda, in terms of the time. What happens in terms of the physical picture? Okay, so to get the where, we just plug in to the original function. And now this is tricky. We've been plugging into V to get these signs to figure out the direction. But if we actually want to know where to plot stuff, we've got to go back to the original function. Okay. So we got to plug into this guy to figure out where things are happening. Okay. So I know when the turnarounds are, minus 1 and 1. I want to know where those are. And so S of minus 1, okay, that's going to be minus 1 over 2. So minus 1/2. S of 1, the other turnaround, is going to be 1 over 2. Just plugging into here. Okay. So now we know what happens. We know we start out going left, we go right, and we hit minus 1/2. We end up, and then we go right for a while, and then go to plus 1/2, and then we start going left again. To complete it, let's say, what would be the total distance traveled from t equals minus 3 to t equals plus 3? Okay. All we need to know is the landmarks. And we've actually calculated all of these things. S of minus 3, we already know is, oh no, we haven't calculated S of minus 3. We calculated V of minus 3. Let's calculate S of minus 3. Minus 3 over 1 plus 9. Remember, it's not V, it's the original function. I want to know where all this stuff happened. So that's going to be minus 0.3. S at the first turnaround I already have. That's minus 0.5. S at the second turnaround is 0.5. And S at the end of my journey, if I end at t equals 3, that's going to be, it's the same calculation but with a plus 3, so it's 0.3. Notice the symmetry here. Lots of symmetries going on here. Okay, so now I can actually do it. Let me see if I can do this freehand and see if it comes out at all. Okay, tools, just do this. Okay, so we're going to start out at between 0 and 1/2, and we're going to go left. Right about at 1/2, we're going to turn around, go right. Then again at 1/2, we're going to turn around, and then we're going to end up a little bit to the left of that. That's what it looks like. Start out at minus 0.3, go to minus 0.5, over to 0.5, and then end up at 0.3. So that's the schematic picture of what's going on. How do we figure out how far? I always do the picture first, because now I can add up the legs. Oh, there's a leg right here. There's a longer leg here. There's a longer leg here. Okay. The first leg is 0.5, is minus 0.3 to minus 0.5. So minus 0.3 minus a minus 0.5, and that's 0.2 distance. Okay. Second leg is 0.5 minus, again, a minus 0.5. They're all subtracting numbers on the number line. That's the 1 between minus 1/2 and plus 1/2. That's the longest leg. And then 0.5 minus 0.3, that's the distance between these guys. And that's another 0.2 symmetrically. So the total is 1.4. Again, that's not the answer to the book's version of the problem, because I modified it. But that's the idea. You get these legs of the journey, you add up all the separate legs carefully, and you get 1.4. Whew! These are involved problems. It took a while, but that's where we'll stop.